Here is one triangle. Its sides are 13, 14, and 15. And here are 8 different formulas for its area. Some use a height. Some use an angle. One of them uses a circle. One just counts dots on a grid. They look like 8 completely unrelated ideas. But every single one of them returns the same number. 84. That is not a coincidence. It is a disguise. So let's begin where everybody begins. Area equals 1/2 times base times height. Why the 1/2? Take a second copy of your triangle, spin it around, and slide it into place. The 2 copies lock together into a parallelogram, and a parallelogram is just a base times a height. Your triangle is exactly half of it. 14 across, 12 up, 168, halved. 84. Hold on to that number. Simple enough. But now, here is the catch. Why would we ever need 7 more formulas? Because the height is slippery. It is not one of the sides. It is a line you have to construct, drop from a corner, meeting the base at a right angle. Tilt the triangle far enough and it falls outside the shape entirely. And in real problems, nobody hands it to you. You get 3 side lengths. Or 2 sides and the corner between them. Or 3 points on a map. Every formula from here is a different way to rebuild that missing height. So let's rebuild it, the first way. Say you know 2 sides and the angle where they meet. 13, 14, and the corner between them, which we will call alpha. Drop the height again, and look at the right triangle it creates. In a right triangle, the opposite side divided by the hypotenuse is the sine of the angle. So the height is 13, times the sine of alpha. Substitute that straight into the old formula, and you get 1/2, a, b, sine alpha. Now watch it with our numbers. That sine is 12/13. 1/2 times 13 times 14 times 12 over 13. The 13s cancel. And what is left is 1/2 times 14 times 12. It was base times height the whole time. Good, but now let's take even that away. No angle at all. All you have left are 3 lengths. 13, 14, 15. Nearly 2,000 years ago, Heron of Alexandria solved exactly this. Add the 3 sides and have the total, to get what is called the semi-perimeter. 21. Then subtract each side from it in turn. 6, 8, and 7. Multiply all 4 of those numbers together, and take the square root. 21 times 6 times 8 times 7 is 7,056. And the square root of that is exactly 84. No angle. No height. Only the sides. Now let's change the question completely. No lengths and no angles. Only positions. The corners sit at 0, 0, 14, 0, and 5, 12. Here is the recipe. Write the 3 corners in a column. The x values on the left, the y values on the right. Then repeat that very first corner underneath, so the list closes back on itself. Now multiply diagonally downward. Each x times the y on the row below it. Add those 3 products up. Then do exactly the same going the other way. Each y times the x below it. Subtract the second total from the first, and have what is left. That crisscrossing pattern is exactly why it is called the shoelace formula. Surveyors have used it for centuries to measure a plot of land from nothing but map references. Our 3 corners give 168, halved. 84. Hang on though. Why does lacing up coordinates give you an area at all? Slide one corner onto the origin, and the other 2 corners become arrows. 2 vectors. And in vector algebra, the size of their cross product is the area of the parallelogram those 2 arrows span. That is the same parallelogram we built back at the start. So the triangle is half of it. 14 times 12, minus 0 times 5, halved. 84 again. The shoelace formula was never a trick. It is this, simply written out in full. Now for something completely different. Every triangle comes with 2 circles built in, and both of them know the area. The first is the circumcircle, passing through all 3 corners. Multiply the 3 sides together, then divide by 4 times its radius. 13, 14, 15 is 2,730. Divided by 4 times 8.125. 84. The second is the incircle, sitting snugly inside and touching all three sides. Here its radius is exactly 4. Multiply that by the semi-perimeter, 21, and there it is again. 84. And this one has a lovely reason. Join the center of that circle to each corner, and the triangle splits into 3 smaller ones, each with height r. 3 base times height calculations, added together. Which brings us to the strangest one of all. Put your triangle on a grid, with all 3 corners on dots. Then stop measuring anything, and start counting. Count the dots strictly inside. Count the dots sitting on the edges. The area is the inside count, plus half the edge count, minus 1. 3 inside, 8 on the boundary. 3 plus 4 minus 1 is 6. And it works on our triangle too. 76 dots inside, 18 along the edges. 76 plus 9 minus 1. 84. Georg Pick published that in 1899. No lengths, no angles, just dots. So step back and look at what we actually built. One idea, wearing 8 different outfits. The sine formula rebuilds the height out of an angle. Heron's formula is that same sine formula, with the angle algebraically removed. The shoelace and the cross product are one and the same thing. A parallelogram, halved. Both circles hide it too. The circumradius rebuilds it from the 3 sides, and the inradius is base times height, done 3 times over. And Pick's theorem counts the dots that a rectangle would have covered. Every road leads back to a rectangle, cut in half. Mathematics does this constantly. What looks like a pile of unrelated tricks is usually one deep idea, viewed from different angles. So, to bring it all together, next time someone hands you a triangle, the real question is not which formula to memorize. It is, what do I actually have? 3 sides? Heron. An angle? Sine. Coordinates? Shoelace. A grid? Count the dots. They will always agree, because underneath, they were never truly different. If you enjoyed watching one idea wear 8 disguises, subscribe. There is plenty more where that came from.